Need to find minimum or maximum instantly? Here's the secret data structure you need to know. Let's start with a problem. Regular queues process elements in first in first out order. Everyone gets served in the order they arrived. But what if elements have different priorities? Imagine a hospital emergency room. You can't just serve patients in the order they arrived. The most critical patient needs immediate attention. How do you efficiently get the highest priority element without searching through everything? You can't afford O of n time for every operation. That's way too slow. The solution is a priority queue, implemented using a heap data structure. So what exactly is a priority queue? It's a special data structure where each element has a priority value. The element with the highest priority is always served first, regardless of insertion order. Think of it like a VIP line at an event. VIPs get served first, even if they arrived last. Now, how do we implement this efficiently? That's where heaps come in. A heap is a complete binary tree with a special property. What's a complete binary tree? It's a tree where every level is fully filled, except possibly the last level, which is filled from left to right. Let me show you an example. Imagine we have the value 10 at the root node. This is our maximum value in a max heap. Below it, we have two children, 8 on the left and 7 on the right. Node 8 has two children of its own, 3 on the left and 5 on the right. This forms our complete binary tree structure. There are two types of heaps. In a max heap, every parent node is greater than or equal to its children. So if the parent is 10, both children must be 10 or less. This means the maximum value is always at the root. In a min heap, it's the opposite. Every parent node is less than or equal to its children. This means the minimum value is always at the root. You can quickly access either the max or min depending on which type of heap you use. Now let's talk about the operations and their time complexity. First, inserting an element. When you insert a new element, you place it at the next available position to maintain the complete tree property. Then you bubble it up by comparing it with its parent and swapping if necessary. This bubbling up process takes O of log n time because the height of a complete binary tree is log n. Second, extracting the maximum or minimum. You remove the root, which is your max or min value. Then you take the last element in the tree and place it at the root. Now you bubble it down by comparing it with its children and swapping with the larger child in a max heap, or the smaller child in a minute heap. This also takes O of log n time. Third, peaking at the maximum or minimum. This is the easiest operation. You just read the root value without removing it. This takes constant time, O of 1. No traversal needed. Now let's see how to implement this in Python. Python has a built-in module called heap that implements a minute heap. First, import heap. Then create an empty list to serve as your heap. To add elements, use heap.heapPush. Let's push the value 5. Then push 1. Then push 3. The heap automatically maintains the heap property after each insertion. To extract the minimum value, use heap.heapPop. This removes and returns the smallest element, which is 1 in our case. The heap automatically restructures itself to maintain the heap property. By default, Python's heap is a minute heap. But what if you need a max heap? Simple trick, negate the values when you push them. Instead of pushing 5, push -5. When you pop, negate the result to get back the original value. This effectively turns the min heap into a max heap. So when should you use a priority queue? Here are the main use cases. First, task scheduling with priorities. Operating systems use priority queues to decide which process should run next based on priority levels. Second, Dijkstra's shortest path algorithm. This famous graph algorithm uses a priority queue to efficiently find the shortest path between nodes. Third, solving top k problems. If you need to find the k largest or k smallest elements from a large dataset, a heap of size k is the most efficient solution. Fourth, finding the running median. By maintaining two heaps, a max heap for the smaller half and a minute heap for the larger half, you can find the median in constant time. Let's recap the power of heaps. Peak at the maximum or minimum in O of 1 constant time. Insert a new element in O of log n time. Delete the maximum or minimum in O of log n time. Compare this to a regular array where finding the max or min might take O of n time, and you can see why heaps are so powerful for priority-based operations. Heap up your knowledge. Follow at srj.learn for more data structures and algorithms. We post new videos every single day. See you in the next video.